just checked for like my side.
This meeting is being recorded.
And it says that I can start the quiz. I don't know if that's just for you, but I can start it.
Probably just because I'm the instructor. Yeah, that's probably why. Well, there should be a button there that says start the quiz. So here, if I go back to my instructor view, then at least I can show you what it looks like here. No, I guess that's not what I want to click on. Because that, oh no, this is edit it. Yeah, I want to edit it.
Oh, wait, we're in chapter 2?
Yeah, we're kind of skipping chapter 1 because chapter 1 is basically algebra review. Yeah, so there's really no assignments for chapter 1. We're just gonna skip it. We'll do algebra review as necessary along the way. Okay. So this is not what it's going to look like for you, but at least from this perspective, you can see the questions. These are all true-false problems. The quote correct answer to all of them is true, because that's how you get points. So basically, you're going to be giving yourself a score out of 10. This is a self-reported grade, and this is just a mechanism for you to put that grade in the grade book, so that I don't have to do it. So what you want to do is you want to answer true for all of them up to the percentage that you've completed. So if you figure, and I only did it in like, increments of 10, just because we're just numerous 10.
Oh, wait, so is the homework talking about the exercise that we did?
No, an exercise set that you turned in last night is different. This is the homework that's from the textbook. Okay, so this is a different component of your grade. Does that make sense? So you have the exercise set that was a document that I gave you, but then you also should be going to the OpenStax textbook and just scrolling to the bottom of the section and doing the homework problems that I assigned.
Wait, is it for free or do I have to pay for it?
Oh, no, it's totally free. It is free, my friend. It is this textbook. It's on the internet. Yeah. Okay, so there's links all over the place. There's links on D12. There's links in the syllabus to this textbook. So like, for example, the 2.1 homework, here's section 2.1. You can read it. You can look through the examples, read the definitions and things. There's a reminder of what slope is. This stuff should look familiar because we were doing this yesterday in class, right? So secant lines, finding the average velocity, that is related to the idea of tangent lines. I think I mentioned the idea of velocity, though we didn't really do an example. Now, this second section we didn't go over. We talked about. This section in the textbook goes over like area. I didn't talk to you about this yet, so I saw that there's a question in the chat, and I'm wondering if it's about this. If it's about this, then that's okay. But here we go. So here at the bottom of the section are the exercises. So this is where you find the homework and the exact problems that you are supposed to be working on, like the ones that are assigned, are written in this document. I'm just gonna show you the document. I know we got a bit derailed. I was trying to show you the homework quiz, but I just want to make sure everybody understands this. So I put a link to it right here in the information widget. See homework? That doesn't actually take you to the textbook. It just takes you to this document where it says which problems to do. Okay, so like 2.1, you do those problems. Make sense?
Yep. So we're going to be doing 2.1 and then part of 4 and then go back to 3 and then continue with 4.
Oh yeah, yes, you're right. Yes, sorry, I didn't mention that yet. But yeah, we're gonna go and dip into chapter 4 just for one section, because that section, in my opinion, should actually be in chapter 2. It's about limits, which is the topic of chapter 2. I don't know why it's in chapter 4. I really don't. It doesn't really belong in chapter 4. It doesn't really rely on chapter 3 or anything else in chapter 4. It's vaguely related to another section in chapter 4, but I think that it really belongs here. So we're going to do it in chapter 2. Yeah. All right, so just the last thing before well, going back to what I was saying and showing you here, this is not what it's going to look like, but you see what the questions are like, right? I completed at least 10% of the assigned homework problems for this chapter, right? So the idea is if you completed 50%, this is true. So check true. The second one is also true because you did complete at least 20%. You completed at least 30, at least 40, and at least 50. So you check all the way up to there. Then that would give you 5 of the 10 points, right? And then if you didn't, I think you can just leave them blank and submit it, and it'll tell you there's some blank ones you skipped, and you can say, yeah, whatever. Or if you want, you can check false for all the rest of them so that your score ends up the way it should be. Now, obviously, this is like, it's really easy to cheat, but I mean, it's a self-reported grade. I mean, you just report your grade. like obviously you can cheat, but don't, right? Like, just, be honest so that I have I mean, it's only 5% of your total overall grade, all right? So it's not huge. So there's really no good reason to cheat. I think it's more important that you be like accurately communicating to me how much of the work you're doing, so I have an understanding of like where you're at and whether you might need more practice, so I can coach you. Okay, I want to be able to coach you appropriately. Make sense? So if you're struggling, not doing the homework would communicate that to me, and then I can reach out to you. See how this works? All right. I'm not saying that is the best way to tell me that you're struggling. I think the best way to tell me that you're struggling is just to talk to me about it. But like, some people are too nervous to do that. And so, this is another way that I could, paying attention to homework completion is another way to keep tabs on you and just look after you. All right, so there is a specific question about a problem on the homework. So let's address that next. So going over here, it's the last problem I assigned on the homework, and it's number 17. And okay, no, you guys can do this one. So I was worried that maybe I had assigned you guys one of the area ones, but I don't think I did. No. So yeah, so in number 16, you're like calculating out the average velocity on different intervals. So like from 4.99 seconds to 5 seconds. So you would use this is your function. You're trying to find the rate of change. So you're basically doing like a slope formula on this problem, just exactly like we did yesterday in class. And so you're gonna be calculating a bunch of different like average velocities, which equates to the slope of secant lines. Okay, so maybe I can draw you a picture of this on my other screen. But then what 17 is asking about is sort of like based on the numbers you got in 16, what do you predict is the instantaneous velocity, which equates to the slope of a tangent line. Okay. So this is just a prediction based on the values you were seeing over here. Does that make sense?
Yes.
Yeah. And would we use the limit like function thing that you showed us how to do yesterday for 17?
You could, yeah, you could write that down. So let me take this over to the other screen. Okay, so now you guys should be seeing my whiteboard. Is that right?
Yeah.
Lovely. Yeah, so so on this, hang on a second, just got to move some things around here. There we go. So on this problem 17, right, you have this S of t equals whatever. Right. And in number 16, you're using the average speed, which is going to equal like change in position over change in time. So this is going to be like a S of x2 or t. I guess it's not called x in this problem, it's called t. So S of time 2 minus S of time 1. S is the position function over here, right? Over t2 minus t1, right? I just want to point out that this idea of average speed or average velocity, I should really use the word velocity here, not speed. I'm sorry. But this average velocity, this is the same as the slope of a secant line. And then the corresponding to that, the slope, the instantaneous in number 17, get my numbers right. You're talking about the instantaneous velocity. At t equals 5, right? So what you're doing here, this is going to be equal to a limit as t approaches 5 of S of t minus S of 5 over t minus 5. So basically, it's like this this whole, this formula for the average velocity, you're taking the limit of that formula with using 5 in particular as one of the two endpoints. And you're having the second endpoint, the other one besides 5, right? The other number, get closer to 5. So it's like you're taking that interval and you're crushing it down to get closer and closer. So you're taking smaller and smaller time intervals, getting closer and closer to 5. And this is the limit notation. So you can use this limit notation when you write out the problem, and then your answer would go here. And that answer should be a constant number, right? A value. You might want to round it to a couple of decimal places or something if it's a bit messy. All right.
Quick question.
Yeah.
Do you have like a preferred amount of decimal places that we should round to?
I'm really not super picky about it, but usually I go to 2 decimal places, so that's to the nearest 100th. If in doubt, 2 decimal places. I don't really care about stuff like what's it called? What's that thing that science people use?
Sig figs.
Thank you. Yeah, sig figs. I don't really care about sig figs. Like, not that they're not important. Sig figs are important in science, but I don't really give a shit about it in math. Like, doesn't matter, because math is way more abstract and like we're just like focused on concepts. And sig figs are more of an application thing. It's like when you're applying math to the real world, then you might want to worry about sig figures. So I'm just going to leave it to the physicists and the chemists and the biologists or whatever to teach you about sig figs. That's not what we're focused on here. Okay. Cool. All right. So let's move on. This is good. It'll take a little bit of time for questions at the beginning of class. It's good, but I do have some other stuff I want to teach you today. Okay. So let's see. Oops, hang on. Oh, hey, Robin. Just a second, guys. All right. Hey folks. Sorry about that interruption. Okay. So I'm going to clear this page and get a new blank page for our section 2.2 for the lesson. Okay. I'm not going to bother saving this one. That's fine. You guys got it in your notes? Going once, going twice. Here we go. Okay, so yes. Oh, go ahead.
Is there a due date at all for the homework?
We went over that earlier. Yep, that's January 24th. It's in the syllabus. Please look over the syllabus.
So it's only chapter 2?
Yeah. And it's only sort of a due date. So read the details. Okay. Okay. So section 2.1 was about tangent lines, right? That was mainly what we were talking about. I want you to know that we are going to step away from tangent lines right now, and we're going to get back to tangent lines later, because tangent lines are related to a concept called a derivative, and the derivative is the topic of chapter 3 and 4, and most like everything else in calculus. So what we're going to do for chapter 2 is step away from that specific concept and instead start learning about limits more in general. So section 2.2 is just about the general concept of a limit. Okay, so yesterday we saw our first example of a limit. Today, I'm going to do some other examples. Oops. Actually wants to be a 1. So this is the first limit example I want to look at. So what does this mean? This basically is asking the question, what y value is the expression log of x over x minus 1 approaching as the x values approach 1 from the left and right sides? Question mark. So that's what this limit represents. It is the number that this function log of x over x minus 1 is approaching as x gets close to 1, right? Because it says 1 right here. Now, from the left and the right, this is what's called a two-sided limit. In a couple of minutes, we'll look at one-sided limits, which is a slightly different thing. Okay. So in general, if not specified otherwise, a limit is always two-sided, which means you have to consider what happens as x gets close to 1 from the left and what happens as x gets close to 1 from the right. So graphically, we can picture it like here's x equals 1 right here on the x-axis. And then our function is doing some other thing like that. And the question is, what's going on? What's going on right here? And what limit are we approaching over here? So it's a little bit different than just saying, what is the value of the function? So, I mean, here, let's do this in two different, let's color code this. If this is an actual point on the graph, I'm going to make it blue. Then over here, this is f of 1, right? Where let's say this is our function. Let's say that there is f of x. Okay, so this is the graph of f of x. It looks something roughly like that, by the way. This is pretty close to what that graph actually looks like if you put it into Desmos or a calculator or something. So that value, if that exists right there, if like there's a point on the graph there, then it has a y value. That's not what the limit is. The limit is about what happens as x gets close to 1 from the left side and the right side. Okay, it's like x values are approaching 1. And as that happens, the point on the graph will approach something, maybe. And this point on the graph, this graph will approach something from this side. So we have x values getting close. The points on the graph are approaching something, and then the corresponding y values are approaching something as well. And whatever they approach, that is the limit. And that's called, we'll just call that L for limit for now. L. Does that make sense? Maybe not, because right now, based on my picture, it seems like the function's value, f of 1, and the value like of the limit, it seems like they're the same based on this picture. You get what I mean? And spoiler alert, for the vast majority of functions that you are used to looking at, and the vast majority of possible x values you could attempt to find the limit at, they are going to be the same. But they're not always the same. And here's why. For this particular function we're looking at here, what is f of 1?
Undefined.
Undefined. That's right. So in this graph, to make this graph look correct, actually, I should erase that point. What we have there is not a point on the graph, but in fact, a hole. And this is undefined. But that doesn't mean that the limit needs to be undefined. The limit can exist even when the function does not, because the limit only depends on the behavior of the function as you get close to that x value, not the behavior of the function at that x value. See what I mean? So the fact that this function technically is undefined when x equals 1 does not mean that the limit doesn't exist. The limit might still exist, and in this case it does. So let's calculate that limit using technology. There we go. I like it to be, there we go. That's pretty good. So here's how we can calculate that limit. What I would recommend doing is actually defining the function explicitly in Desmos. Okay, and by the way, a lot of you are using like a TI calculator, and you're probably just like used to using a TI calculator because it's comfortable. But I genuinely recommend that you get used to using Desmos, because I think it's just a better tool in almost every way, at least for learning. TI calculators are slightly more powerful, technically speaking. There's some things they can do that Desmos can't do, but not a lot. and like they're much more clunky and harder to use. So yeah, I do recommend using Desmos for the sake of learning. One of the things that you can do in Desmos is define functions. And so I am going to define a function. If I type / right here, then I get a fraction, okay? And I can put log of x in the numerator. This, by the way, is log base 10. If you were wondering, this is the common logarithm here. And then x minus 1. I am assuming that everybody has studied logarithms. That is a prerequisite for this course. If you haven't studied logarithms ever, that's gonna be a problem, because I'm not planning on teaching you all about logarithms. You should have already learned that. That's definitely a prerequisite topic. Logarithms and exponential functions. If you don't remember it very well, that's fine. I can remind you. But if you've never learned it before, then like you should probably be in pre-calculus right now. So just putting that out there. Don't expect me to teach you what a logarithm is. I'll remind you, when we have time. All right. So there's our function, right? So then what you can do in Desmos is you can plug things, you can reference that function. Once you've given it a name, like now it's called f, I can say f of 1. Oh, it's undefined. That's right. It's undefined. But if I said f of 2, aha, okay, there we go. So f of 2 does give me a number, right? I could call this something else, like I could call this G. And if I call this G, then it doesn't know what F is. And it thinks maybe Desmos is thinking, maybe you wanted F to be a variable. So like, should we give you like a slider for that? So you can change the value? No. I wanted it to be a function. So now I've called it G. Now it's G, right? So I'll just go back to F again. So whatever you call it, that's what you can refer to it as. And Desmos will remember. It's like a programming language. Okay. So F of 2. So what I really want to do is I want to start doing some numbers that are like close to 1. So f of like 1.1 and f of 1.01. And you know what? Let's just do a table. Let's just do a table. If I press plus, I can insert a table. I can have my x values, and then over here I can erase that y1 and I can write f of x. Let's just call this x. Instead of x1, I can just call that x and f of x. So now I can do a table of values. So let's do like let's do 0.9, 0.99, 0.999, 0.9999. There we go. And then I can do like 1.0001 and 1.001 and 1.01 and 1.1. So now we can see the trend. Okay, I need to scroll this out a little bit. Let's see. All right, so now I can see what these numbers are approaching. My limit should be somewhere in between these, right? But I can see as we get close from one side, it's 0.45, blah, 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 and then it's 0.43, blah, 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 0.43, blah, 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 0.43, blah, blah, blah. As soon as it starts to repeat itself, then that's, it has reached that level of precision. So it looks like we have the best precision we have here is about 0.434, right? I think the best we can do is say that it's about 0.434. If I wanted more precision than 3 decimal places, I'd have to keep going because I don't see it. It's not repeating itself because the previous one was 0.4345 and this one is 0.4343. So it's not clear yet what that 4th decimal place should be. I need to go again, right? Now, maybe we'll get more information from the other side, right? If we go from the other side, 0.41, okay, 0.43, that's good, 2, and then 0.434, and then 0.434. Okay, so the 0.434 sounds pretty certain, right? And it looks like based on this, the next decimal place is probably a 3, but maybe a 2. Actually, maybe it's more likely to be a 2. I really don't know. It's not clear what the 4th decimal place is yet. So I'm just going to go with 0.434. Okay. So it looks like that's what we're approaching from both sides. And so based on that information, I can guess and be fairly confident that this equals 0.434 approximately. Probably. Right? I'm stressing that what I have shown you how to do here is not a rigorous calculation of the value of this limit. It is just a guess based on what the trend in the numbers, right? Okay, so is this making sense so far?
Yes.
Else? Okay, let's look at a second example. Let's look at the example limit as x approaches 0 of the absolute value of x divided by x. This is an interesting function. The absolute value of x divided by x. Okay, if I
Quick question.
oh sure.
Does it matter what you put as? Does it matter what x is approaching?
Well, yeah, it's specified, right? So like this limit was as x approaches 1.
Yeah.
So, I
Okay,
mean-
so it's whatever's in the parentheses kind of thing.
It's whatever's down here. Yeah, it's x approaching whatever. So like we're gonna get a totally different number if we have x approaching something else. So like going back to Desmos here, if I had picked numbers getting close to 2, now here's some numbers getting close to 2, and you see I have a completely different. Oh here. No, we're getting different numbers, right? See that?
Yeah.
But yeah, this is like 0.3, 0.301 about. So like, it definitely matters what that number is.
Right. So the number that is like the decimal that is most nearest to a 1 or 2, like for example, if it's 5 and the decimal like 4.5 now 4.999999.
Yeah.
If it was like that, then that would be its answer. Like if you were to find f of x of 4.999, and then you get the answer for that.
That would be that you would be looking for the if you were using these numbers where where the numbers are really close to 5, right? This is sort of like getting close to 5 from the left side, and this is getting close to 5 from the right side. Then yes,
you plug
would
it
be getting.
And then you plug the x's into the equation.
Yep. Yeah, this is all being plugged into F here, right? It's all being plugged into F, and these are the outputs. So this is just what your calculator would give you if you typed them in individually. It's just quicker to do it in a table. Right? Yep. And so this number, this is 0.175-ish, like that number is that's about the value of the limit as x approaches 5. So that would be if there was a 5 right here. That make sense?
Yeah.
Yeah.
Cool. Yeah, so for this one, I need to change my function to an absolute value of x over x, and I need to change my table so that I'm approaching 0. So let's go back to Desmos and do those two things here. I'll scoot this over. And then, yes, so first of all, let's change this function. This is supposed to be the absolute value of, no, hang on, it didn't work. Let's just delete it. Delete it all. Okay, fraction, we want absolute value of x divided by x. And then this is not what I want. I want like negative 0.1 and negative 0.01. This is how you do it when it's getting close to 0 from the left side, right? Like this. Oh my gosh, it just all says it's -1. That might make sense. And then we've got positive 0.0001, right? And positive 0.001. I always do that. You always want to do a trend. In this case, the trend is the constants. Oh, what is going on here, my friends?
Both answers, there are two solutions to this, or there's two solutions.
It's either
Negative
with
1
two
and 1.
solutions or
No solution.
no solution, right? So, very astute. Yes, in this case, we say there's no solution. So, when I ask you what does this limit equal, the way we can answer this is we can answer DNE, which stands for does not exist. It is possible for a limit to not exist. Okay, in this case, there simply is no number that the y coordinates are approaching. Because the left side and the right side are in disagreement. They don't agree with each other, right? So in here we have from the left, f of x, our function here, is approaching -1. From the right, f of x is approaching positive 1. These are called limits from the left and limits from the right. They're one-sided limits, but this is a two-sided limit. Like I said earlier, unless specified otherwise, the limit is from both sides, and you have to look at it from both sides, and you have to make sure that those are the whatever the outputs are approaching is they are in agreement with each other. Because if they disagree, if one of them is saying, hey, I'm approaching 5, and the other one's saying, hey, I'm approaching 12, then they're going to fight, right? And neither one is the answer. In fact, there's no answer, right? Because they have to be both approaching the same number in order for that to be the limit. All right, so that's why this does not exist. Now, there is a special notation you can use if you specifically want to know the limit from one side or the other. So I'll show you what that is. These
Aren't they
are,
both approaching 0?
sorry, what was that, Frau?
Aren't they both approaching 0 though? Since, I mean, like on one side you have -1, on the other side you have, like, aren't they both going towards 0?
Well, the x values are, right? Because x is approaching 0, but the value of the limit, like the answer to this limit problem, would be what the y value is doing. And the y values are not both going towards 0. One of them is just staying at -1, and the other one is staying at +1. Okay, you were muted, but I saw you talking. So you,
Yeah, like the decimals aren't leading up to something. Like if there were a bunch of decimals kind of reaching toward the middle. Yeah, I got
That's
it.
right.
I got it.
okay, cool, good. All right, so notation for one-sided limits, you just put a little, let's see, if it's from the left, you put a little minus as a superscript, like you do with a power, right? You just put a little minus after the number. So this equals -1, and then if you put a little plus after the number, that means from the right-hand side, and this would equal +1. Okay, by the way, the graph of this function basically looks like this. You might be familiar with this one. It kind of looks like this. So, you know, if your x values are approaching 0, your y values are, your points on the graph are coming in like this, and these y values are here at +1, and these y values are down here at -1, which is why there is no limit. This is an example of a thing we call a jump discontinuity. I'm getting slightly ahead of myself with the vocabulary here, but I might as well tell you. This is called a jump discontinuity. A discontinuity is a point on a graph where it's not continuous, and continuous means that, like, connected, you know, like it's a point where there's a jump, so it's not connected. There's sort of an interruption in the graph, you know, something suddenly happens where it's different suddenly. That's an example of a discontinuity. This, by the way, is called a hole. It's another type of continuity, a discontinuity. There's another term for it, but I'll tell you that later. Like a hole, right? You probably studied holes in pre-calc when you did like rational functions. Did you guys do holes for rational functions?
Yeah, and we did jump discontinuity.
Oh, you did do jump discontinuity. Sweet. Cool. All right. Well, some of you, not everybody, I bet. It depends on where you took your class and from whom. All right, so let's do one more example of this type. Let's look at the example, the limit as x approaches pi of cotangent of x. The limit as x approaches pi of cotangent of x. So it's going to be slightly hard to do, but we can do it. So we can put a cotangent of x in here. All right, cotangent of x. And then over here, we want to have x getting close to pi, right? So like, let's do 3.14 and 3.145 and 3.1415. sorry, 141 and then 1415, 3.14159, and that's about as much as I remember. 3.141592. I guess maybe I can do a little more. So this is not ideal because this is not actually this is really only approaching from the left side, but we could do it approaching from the right side as well. I'm just going to do the left side for now. 3.1415928. Oh, this is kind of weird. I think Desmos might be getting a little bit confused. I think Desmos's computing capabilities are being stretched right here, and I'm gonna erase this one because I think this is like an error. This is a positive number, but it shouldn't be. So I'm just gonna delete that because I think that's just confusing. All right. Okay, so what is happening here? What are we approaching with the y values?
0.
Infinity.
It's not 0. If this was like a times 10 to the power -6, then we might be getting close to 0. But rather than that, these numbers are getting bigger in absolute values. So yeah, I think infinity, or rather, because they're negative, we could say negative infinity. Okay. So put that in the notes here. This is another situation where we can say DNE does not exist, because if the outputs of the function are getting closer and closer to infinity or negative infinity, well, infinity and negative infinity aren't numbers. You may have heard this before. If you haven't, that's okay. Not all courses, not all, not everybody has really dealt with infinity before calculus, so this might be a very new concept. But infinity is sort of an idea, but not a number, right? I like to think of it as like a direction. Like infinity and negative infinity are like east and west. You could say, I'm going towards that. I'm going towards infinity. I'm going east. Or I'm going towards negative infinity. I'm going west, right? Whichever way. And you can't ever arrive there, right? You can't ever get to east. It's not a place. It's a direction. That makes sense? And infinity and negative infinity are kind of like these hypothetical things at the end of an infinite train line that you can never get to infinity and negative infinity. They're not numbers. That makes sense? So those are so if it appears to be approaching infinity, then that means that it doesn't exist. And that's the case on this one. So there we go. So we've seen a few more examples of limits. We're just going to carry on with this section. Tomorrow in class, we're going to be focusing more on looking at graphs and less at looking at numbers. Okay. So have a great day, everyone. And if you're not already, take a look at those homework problems and spend some time working on those. See you tomorrow.
So yeah, have a good one.
Oh, Ali points out that I forgot to take attendance. Oh, I did. Well, I didn't really. No, I was going to look back at the chat and take attendance. So I'll do that now. If you didn't say that you were here earlier, then you can do so. As long as you've posted something in the chat, I think you'll be fine.